you is the second talk of this morning section. The talk will be by Ferry Kwakkel. He's at IMPA now, and he's going to talk about the dynamics of non-resonant torus homeomorphisms.
Okay, thank you for inviting me to speak here today. It's a pleasure. In honor of Maurício, I don't know if he's here yet, but I'm sure he will come in any moment. So, dynamics of non-resonant torus homeomorphisms. So what does non-resonant here mean? Well, I'll first start with a little bit of history to explain it. So if you look at dimension 1, and you look at circle homeomorphism, say, let's stop to the identity, with no periodic points, then, and this is of course due to Poincaré. He was the first to get the global picture here. Then there exists a rotation number, which just sort of measures how much points are moved in the lift on average. So this is an element of Q. Sorry, not an element of Q. And that's if and only if you don't have periodic points. And let's call this number here alpha. So he said that either one of two things can happen. Either one, phi is transitive, so there's a dense orbit. And in that case, he said it's actually minimal. And so the minimal set here is the whole circle. And what's more, there exists a conjugacy to the rotation with rotation number alpha. Alpha the same. This is alpha here. Or 2, well, phi is not transitive. And in that case, there is a Cantor minimal set. In either case, you do have nice orbit structures. So the minimal set equals the non-wandering set, and that equals the alpha and omega limit set of every point in a circle. So that's nice. So now what about dimension 2? Well, things get a bit difficult. You can try to say, well, suppose I have a homeomorphism now on the 2 torus without periodic points, or just any homeomorphism isotopic to the identity of the 2 torus. And you can say, well, what's the rotation set now? This is, of course, mod. Well, the rotation set is taken mod set squared. So here, in general, this is no longer a single point, so this is a convex closed set. And so that's certainly different from dimension 1. And 2, even if rho of f is nice, and by nice, for example, you could say it's an irrational number. Well, let me just say nice for now. I will make that precise later. So even if rho of f is nice, there does not exist a semi-conjugacy to a linear model. Okay. So basically you have to make a choice here. What do? You have to choose a nice family of torus homeomorphisms. So in the past 5 years, there's been a lot of progress on this. Just to mention 2, there's a group from CNRS in Germany, roughly, and they study what they call quasi-periodically forced circle homeomorphisms, which are basically just skew products of the following form. xy goes to x plus alpha, this psi xy. Alpha here is non-rational, so that's where the forcing comes from. Not in Q. And so for every fixed x, this is just a circle homeomorphism. So, well, a lot of work has been done here in this case. So I think it's important to just mention a couple of names of people that have done a lot of work here. Began. I'll not be complete, but I will just try to write down Stark, Keller, Jaeger, Corviget, not the least. And I think Leroux. Okay. So that's in this setting. Tobias Jaeger independently looked at conservative, meaning it preserves the back measure, torus homeos. And he gave a very nice sort of Poincare-like classification. Of the dynamics in that setting. So, a lot of good work done. I will focus on what I call non-resonant torus homeomorphisms, which is not conservative, nor is it of this form in general, but there is certainly overlap. And I will use that overlap because their work will come in later in what I will what I will do. So okay, so what's a non-resonant torus homeomorphism? Let me write this. So non-resonant here means the following. I'll denote it by homeo star. So that's the class of torus homeomorphisms as a topic to the identity. Sorry?
What did you just say?
Oh. Homeo star, this is the class of non-resonant torus homeomorphisms by definition. So these are the F isotopic to the identity, for which the rotation set is a totally irrational vector. Where by totally irrational I mean that 1 alpha beta are rationally independent. So that's the class we'll focus on. So now what's the main question we want to answer? So the main question here is what are the possible minimal sets? Minimal sets. And relate these to the non-wandering set. And the alpha and omega limit sets of individual orbits. Points in the torus. Okay, so in order to first give a rough classification, need a couple of definitions and notation. So the first is, I will say that X in the torus, a connected set, is bounded or unbounded according to whether the lift is bounded or unbounded. I will call a disk in the torus. The injection of the disk, unit disk, say, in the plane by a homeomorphism into the torus. And similarly, so this would be a disk and an annulus. Yeah. So an essential annulus, similar thing. Just take the injection by your abstract annulus by a homeomorphism into the torus. So one more notion before I can state first result is the notion of so much of what I'll be talking about will be stated in those terms. There's one more notion, it's called an extension of a Cantor set. So it's roughly speaking sort of a blown up Cantor set, if you will. So what's an extension of a Cantor set? So suppose you have M, which is a minimal set of a non-resonant F. Now suppose you can write M as a disjoint union of bounded continua. And now define the filled-in minimal set, the disjoint union of all the components when filled in. It's just a filled in, some kind of, just fill in the stuff. Now, if there exists a phi of the torus to itself, continuous, I stop it to the identity. There exists an F prime, non-resonant, such that the following holds. Here is your original F. Oh, sorry, this means non-resonant. And this means the filled-in set. Oh, the quantifier, right. So let M be any minimal set, okay? And suppose you can write it as a disjoint union of all these bounded sets. Fill all of that in.
What is the fill-in?
The fill-in? Well, because it's bounded, you can pass to the left and fill in there.
What you're saying is just a connected set, right? So continuum means just a connected set, right?
Right, closed.
Closed connected set, so what is the fill-in? In the plane, what is the fill-in?
Well, there's one unique unbounded set, and there are like a bunch of bounded disks.
So this is a multiply connected domain?
Right. Well, no, I mean, because this is a minimal set, that would be like nowhere dense. I mean, this is a closed set, it's not a open set.
So what's the fill-in of the standard Cantor set in the plane? Well, that's not connected.
No, right, yeah, that's the point. I mean, those are just points. So if you have larger sets, closed sets, then it may, I mean, just take a circle, for example, you can fill it in. Right? So if I have a closed set, and I take it to the left.
If I have a closed set which is connected.
Right. And then then you have one, unbounded open set in the complement of that closed set. Plus you can adjoin a number of open disks, open cells to that closed set, and that's the fill-in.
It's the smallest.
Right. Yeah. It's
the smallest set which containing the set that you have with by one together.
that does not separate the plane.
For example, how do you feel the
Yeah, yeah. Well, if you lift that, that's like an unbounded closed set. That's not a bounded set in a lift. If you take, Sierpinski cup, well, depends on whether you define it in the plane. So you would have like this, like the plane minus the, square. Then you just fill in all the disks. So you just get the closed square, basically, right? So NR will stand for non-resonant. I have a semi-conjugacy here, F prime. So if there exists a phi continuous, so here this is semi-conjugate, such as phi sends the filled-in minimal set to a Cantor set, and C is a minimal set for F primes, then we say F is an extension of a Cantor set. So you just sort of fill in all the rubbish and you quotient that out. So if that is a Cantor minimal set for that vector, then that minimal set upstairs will be an extension of a Cantor set. You see, the point is that you can actually really blow up a Cantor set. So you can have arcs and circles and dendrites, and I'll basically get to that. But you can have all sorts of stuff sitting there in the lift, and you can't really quotient that out without filling it in first. You get a bubbled surface.
How do you quotient it out?
By more. Once you've filled it all in, you can do like a quotient by Moore.
What's that?
Moore's theorem, saying that any upper semi-continuous decomposition of the plane can be quotiented out by a continuous map. So it basically takes these so phi here takes the filled-in sets. It takes these filled-in sets to points. Yeah. Yeah. And so, as I say, if you would have stuff with holes, that wouldn't work. You get like a bubbled surface. So you first have to fill it in, and then you have to pass through this, quotient. So that's an extension of a Cantor set. So now what can we say about the minimal sets in terms of these definitions? Well, basically three types. Sorry? M is the extension. Then M is an extension of a Cantor set. Of a Cantor set. Okay, so your Cantor set lives here, and M lives here. Okay? So you fill M in, quotient it out, and you get your Cantor set here. And so this is a Cantor minimal set for this vector here. And this M is a minimal set for this F here. But if you fill it in, it's not a minimal set for F anymore, of course. But you need it in order to sort of, quotient it out. But it will be a minimal set for this Cantor set. This image on the phi, which is a Cantor set, will be a minimal set for this vector. No, well, yeah. So there exists a phi and there exists a F prime. There exists. So that goes through the whole sentence, yeah. Yeah. And because all these lambda I are bounded, you can do that. If it's unbounded, that isn't really well defined. I mean, what's the fill-in? It can be like a line, for example. It doesn't make sense. Okay. So now, let's make a list of the possible. It's basically theorem slash definition. So the classification of minimal sets. So let F be an homeo star. It's non-resonant. And M a minimal set, where I assume M is not the whole torus. So then either there are three possibilities. Either one. Oh, and I should say let sigma k be the connected components of the torus minus the minimal set. Okay? So that will either be, well, one, sigma is a collection of disks. Two, you have annually in disks, but I really want that to be annually, essential annually. Disks. And three, that's your extension of a Cantor set. So I should make a couple of remarks and see what this means basically. It's sort of a rough statement anyway, but if you observe a couple of things, I think things become more clear. But I would have to say that follows more from the proof than from the statement. Oh, non-resonant means there's a single rotation vector which is fully non-rational. That's all. So let me make a remark. So you can show, I'm not saying that here, but you can show that bounded disks always wander. Essential annually always wander. Sorry? Yeah, but it can be an unbounded disk. If you take a lift, it can be like an unbounded disk. So it's an open disk, embedding by a homeomorphism of an open disk, but not a closed disk. In the lift, yeah. And unbounded disks may be periodic. Okay, so let's write down a couple of corollaries. So which minimal sets are connected? Well, you can sort of eyeball what you have. Well, if you have a Cantor set or extension thereof, that's not going to be one connected component. Essential annually, well, if you have one, then you have a whole bunch of them. So that will separate things. So the only possibility is type 1, and that's an if and only if. If you cut away disks from a torus, no matter how ugly, that will always be one connected component. So M is not equal to the whole torus connected, if and only if, so type 1. Okay. So the second corollary, this is something that I was basically always interested in, the orbit structures. So what can you say about the orbit structures? Well, let me first make the statement about type 1 and type 2. Type 3 is different, as it turns out. So remember that in dimension 1 you had a unique minimal set which equals the non-wandering set, and every limit, every orbit limits on that same unique minimal set. So that's still true in type 1 and type 2 in dimension 2 here. So if your minimal set M is of type 1, type 2, then you have that M equals a non-wandering set. It equals the alpha and omega limit set for every z in the torus. In particular, M is unique. So that's nice. Things behave quite well there. So what about type 3? Well, let me state it as a counterexample. It's not true. So this was done by some of the guys I introduced earlier. Began, Croviget, Jaeger, and Leroux. What they showed was that there exists, in fact, type 3. I mean, they don't call it type 3 anything like that. So what they do is in the setting of these skew maps. So in that setting, they construct, but it's still, I mean, it's still a non-resonant homeomorphism. So that's the overlap we have here. What they showed is that there exists F non-resonant, where M is the unique minimal Cantor set, but there's also a dense orbit. So the non-wandering set is the whole torus. So non-wandering set is the whole torus. So type 1 and 2 things behave well, and type 3 things may or may not behave well. Sometimes it does behave well, sometimes it doesn't. So, one more thing, what about locally connected minimal sets? As you can perhaps guess from the list, things would reduce a little bit if you would require your minimal set to be sort of nice from a local topological point of view. So notice, by the way, that sort of the global orbits, I mean, if you for example, just take a bounded disk, that may be a very nice disk, or it may have all sorts of ugly, boundary. But basically, the global, orbits don't really see that local ugliness. This can be very ugly or very nice, but things sort of always behave well. So that's, in a sense, sort of a globally induced thing. Yeah, no. Well, what do you mean? The type 1 and type 2? What remains? Well, not too much is known there. I will talk about C0 examples, see how far we can push things there. Pretty far. Basically, everything that I've been talking about, you can actually do. So you can really blow up Cantor sets and stuff like that. But when you can, no, I didn't say C. I didn't say C. So, oh, not C not. Sorry, C not. Yeah. Oh, sorry, homeomorphisms. Yeah. Okay, so what if we require the minimal set to be nice topologically? So that's measured, I guess, by locally connectedness. So if your minimal set is locally connected, there's basically roughly only one type. Then that means that M is a quasi-Sierpinski carpet, as I call it. It's almost a Sierpinski carpet. So what that means is that you have a union of disks, dense in a torus, and this is dense. So if the closures of any two disks are disjoint, then it's a Sierpinski set. But if you allow, so the closures disjoint Sierpinski, but if you allow two disks to intersect in a single point, at most, that's a quasi-Sierpinski set. And again, that can all happen. And that would still be locally, connected. But anything more than that, you're out of the game, basically. So this is everything that remains if you want your minimal set to be nice locally. And again, you can sort of, if you look at the list, it's almost obvious, I guess. I mean, certainly this wouldn't satisfy this, the Cantor set, or any blow-up of this. Annually, well, if you have one, then you have a whole series, and they all limit on one another, so that's not going to work either. So you have to have a torus minus disks, and then you can argue that the disks have to be nice, and when you keep on talking for a while, you basically end up at your quasi-Sierpinski carpet. Okay. And by the way, in sort of a general setting by locally connected minimal sets have been classified by Bies, Nakayama, and Walchuk. So I want to say a couple of words in what remains about how to construct them. So let me keep that. So what we've been talking about so far basically just talks about abstract properties of minimal sets. But if you give me a non-resonant torus homeomorphism, how can I make sense of what the minimal set is? I mean, is there a nice way of seeing what the minimal set is? Well, in general, I don't know of any such method, but what you can do is look at a natural subclass, and that gives you a nice method. So define homeo sharp. It's a subset of homeo star, non-resonant. So those are the ones that are semi-conjugate, in fact. It's a bit stronger. To in rational translation of a beta rationally independent through a continuous pi. Pi is continuous isotopic to the identity. Now the only thing we want is that the regular set of pi is uncountable. So the regular set of pi is a set of points in a torus on which pi is 1 to 1. Okay, that will give us a clear picture of what is going on. So the number of points in a full preimage is 1. So, and we want this to be uncountable. So, and then by definition, F is in homeo sharp. So now facts, so what does this to do with minimal sets? Well, you can basically read off from what pi does, what the minimal set is. So that's the import here. So if F is in homeo sharp, then F has a unique minimal set. So M. And M is precisely the closure of the regular set. So in other words, if you can keep track of that set of points, you start with a simple model, you blow stuff up. If you can keep track of that set of points, you know what your new minimal set is. And that's basically the game we're sort of playing here. You start with a simple model, and you make things more and more difficult. And just by sort of careful blow-ups, watching where that set of points goes makes that you can understand the minimal sets. So one thing that I would like to say a couple of words about.
Do you have an idea of what's happening on the non-regular set of the preimage?
Well, notice that this is not true in general. I mean, this can be like an empty set in general. There are maps of the torus which every point inverse is an arc, for example. No, I cannot really make statements about what happens there because, for example, the example I mentioned that you have a dense orbit, but that the Cantor set is a minimal set, that's an example semi-conjugate to a translation, in fact. So there you would have a unique minimal set, Cantor set, but you would still have this dense orbit. So you can't really make sense of things there. You can't say that you have these good orbit, structures. They do that, by the way, by using techniques due to Mary Rees. She worked with skew products. You can basically blow up points to arcs and construct very interesting homeomorphisms. So one thing that I would like to sort of single out, one construction, basically using this, is how to blow up a Cantor set. So as I said, basically all these minimal sets actually exist, and before the examples I constructed, there was also an example known, again by the same guys that I mentioned before. An example, again 2009, Biguin, Roviger, Jaeger, Leroux. They constructed a type F non-resonant, a minimal set, consists of so disjoint union of lambda I, where here lambda I are points and arcs. But remember, they have to work with a skew map, a skew product, so that doesn't give them too much freedom. I have sort of the full two-dimensional picture, so I have a bit more freedom to do things. So how do you blow up a Cantor set? Well, they do it by using a technique due to Mary Rees. I do it slightly differently. So how to blow up a Cantor set? So you start with a simple model here. Well, there's a very simple model you can take. You just take the product of two Donjois counterexamples. So F naught, say, is just a product of two Donjois counterexamples. And they have two Cantor minimal sets, C1 and C2. The minimal set here is, of course, just a product of the two Cantor sets. But now there's an issue. Normally, if you blow up points to disks, what happens is that you assume that your mapping is C1. That's how you sort of define the action at your point when you blow up a point to a disk. Now, the point is that if I would assume that phi and psi in the circle are C1, then I cannot choose any Cantor set any longer, right? I mean, like the standard Cantor middle thirds or something can't be made that way. But that's sort of a problem because I want to choose my Cantor set in a good way. I want that Cantor set to sort of behave in a certain way. Only then will that blow up work. So instead of doing a C1 blow up, I do a C0 blow up, which is, it's a bit more difficult. You have to keep track of things a bit better. You cannot just say at a point it behaves like D of F. So we have to work with foliations basically in order to blow up a point to a disk. But you can do this. And now what I claim is that if you do this in the right way, you can blow up these Cantor sets. And so what you do is so since we work now in the C0 category, just with homeomorphism, we can basically choose any Cantor set we want. So since we have the choice, we can choose it to take a canceled minimal set here, C2, so this product, Cantor set. Now, roughly speaking, this Cantor dust, modulo the endpoints, those are the points on which pi is 1 to 1. So if you take your Cantor set and either factor and you take away the endpoints, and you take the product of these two sets, that's your set on which pi is 1 to 1. So roughly speaking, that is your Cantor dust. So if you do the blow up, and you can make sure that all that Cantor dust basically settles on the boundary of that disk, then you know you've done the right thing. The problem is that that wouldn't always work. You can choose a Cantor set or a product for which that wouldn't work. So there's some sort of delicate choices here. But if you do it in the right way, it does work. So if you choose the right point and the right Cantor sets, C1 and C2, and if you take a point, you have sort of this Cantor dust sitting here. If you do this radial blow up, then all that Cantor set will basically limit on the whole boundary circle. And that will also happen for that whole orbit, because you're not just blowing up one disk, you're blowing up a whole orbit of disks. And once you've done that, what you have done, you've made an extension of a Cantor set. And also that blow up gives you the semi-conjugacy, so that's all built in. So what you get is you get Cantor dust in this way, interspersed with circles, or simple closed curves rather. And so every point on the circle is a limit point of pointing your Cantor dust, and every point in your Cantor dust is a limit point of smaller and smaller circles. Now you can quotient this out again, for example, to make flowers or dendrites or stuff like that, where you have again your Cantor dust limiting on your closed sets. So these are basically these lambda i's that I was talking about. And so if you would fill this in, you can quotient them out to points and you get your old Cantor set back again. So what I've done here is basically start with a Cantor set and blow stuff up. And what theorem A basically said was that all extensions of Cantor sets are basically made that way. You start with this sort of blown up Cantor set, and then you can take like a quotient to your normal Cantor set, where basically every lambda I is a point. And so, well, this basically shows that you can really go pretty far with these examples. Now, if you push that, if you do some more work, you can show that basically a lot can happen here as well. So everything that this list basically says could happen, does happen. So you can fill all of this in. So a couple of very quick closing remarks. What I didn't answer yet is following question. Is a type 3 minimal set unique? So are these Cantor blow-ups unique? I don't know. I don't know anybody who does. But recently, Rafael Potri, Uruguay, 2011 on Archive, posted an interesting preprint that basically, it doesn't prove uniqueness, but he did show that all non-resonant torus homeomorphisms are chain recurrent. So they do have a weak kind of indecomposability. It wouldn't show that's unique, but they are pretty nice. And furthermore, and that's forthcoming, it's joined with Tobias Jäger and Alejandro Pasegui. a more general classification of minimal sets. Minimal sets, and more general here means that you allow all torus homeomorphisms, not just non-resonant ones, sort of any homotopy class, everything. You lose information in terms of the orbits, but as far as the minimal sets go, you can really push things through a lot more, generally than I did. And so that's forthcoming. I think I want to leave it here. Thank you.